by all startups.
Yes, I had yesterday.
They just want to find one.
We ended at 19, and then when I got home, I just like. But no, I didn't go to sleep. I had to cook meat before it expired. Fortunately, I have food. I'm just broke.
I mean, it's just, it's so far and it's so cold. So every time I want food, I just make oat and omelette. Okay. Okay, sure. I wish I could get you anything, but if you get something from Spain.
Yeah, someone's here yesterday, but he's
Do you like peanuts? I still have a bunch of yeah, it's like little peanut candy. If I remember, yeah,
question with you. Sorry, sir.
about the game, yeah. Well, we were discussing whether it would be circles or
Yes.
yeah.
I was playing Deadlock. I was playing a character that turns into a ball and a cube. So I was trying. And if you were to choose between being a cube or being a ball, what would you choose?
Cute. I just like my little game. Yeah. I mean, it's
Did you answer I like my cave?
yeah, I like my game.
Me too.
I chose the because it's the game jam.
Yeah. Nah, I would pick. We came to a conclusion that being a group is the best choice because you can turn both into a cube and into a ball. Both.
Yeah, like half. Also, Mark, completely out of topic, but have you seen that Cartuta las Pietas, I think? It's the same like potato pancakes in Latvian.
Oh, well, Kartupelio Pantas.
Yeah, it become like number one in
Cyber-physical systems and IoT devices.
potato dishes.
There's a
And I
ton
was
of
like,
microcontrollers. So if you want to specialize in embedded systems, no worries. You will always find a job. Actually, all companies all local companies kind of in the region. Apparently, we have around 100 software companies. Many of those actually do embedded systems. They will always look for embedded engineers. That's why actually mechatronics is very popular because of the cyber-physical kind of nature. So you have digital and physical mode. The embedded systems actually have a lot of software. What is kind of interesting, I always mention that, but maybe I've forgotten. There's one language that almost died, but is still alive. It's named COBOL. You know what's the problem with COBOL? The people that actually know COBOL and can program COBOL, they are either retired or dead. So there's one way to make money. You learn COBOL and you open a company that actually starts selling their services in COBOL. We expect that in 10, 20 years the same will happen to C. So I can easily retire because I can still do C and C++. I can offer consultants because all new generation kind of we are not going to have the skills, unfortunately. So there will be kind of discontinuity gap. And you know actually why we use COBOL? Because it was one of the first high-level programming languages, I think probably invented, I think it was in the 50s, where people believed that programming languages need to be very verbose and English-like spoken language.
I happen to know that it's from the late 60s and it was only officially released sometimes in the early 70s. I looked it up at one point, so I happen to know that.
I think COBOL actually started, I believe, in the 50s. It was very old. Is it? Okay. I will check my sources. I think it was first done by military people somewhere. Anyway, it's actually used on mainframes. It's used on processing actually money, and it's used everywhere. And you know why? That's actually the most funny story. Why do we still use COBOL? There are AI programs to replace COBOL with Java, C#, anything else. And we still use mainframes with COBOL. Because they work. And they perform. You cannot replace COBOL with Java and C#. This is the biggest joke. There's no computer that can match the performance of computers from 60s. Okay, we improved it, right? Those are specialized computers for kind of performing operations on data. There was also first language that actually could do decimals correctly. You remember first semester computer system course, we had a problem with floating point arithmetic, right, with the precision. COBOL could actually cope with decimals well. But I think the biggest thing is that COBOL is still kind of performant language that is old, like, I don't know, 60 years now, more than 60 years, 70 years? 66. And we cannot kind of transfer that in any modern language on the modern computer. This is kind of really, I think, that should be one of the joke of the century. And now there are programs of using AI to transform. There's also like millions of lines of code. There's also kind of an issue, so don't worry. So anyway, when it comes to challenges of cyber-physical systems, designing actually those, it's kind of a challenging. And the problem comes from the fact that it's not only about functionality, so it's not about features that you need to implement, it's also how you implement them. We typically talk about dependability, so which is related to reliability. So you actually need to design your system well that doesn't take only the functionality but also the characteristic of your system. One thing that this slide also says, and it's very important, is that you cannot add those features afterwards. Typically, if you consider, for example, safety, security, reliability, availability, and there's tons of those, they have to be done at design time. You cannot make a system and then incrementally improve it to make it more secure. This is not going to work. It's the same with safety. Because at the beginning of your project, you probably make decisions that prevent you from changing that afterwards. And I think there's like examples. So for example, if you consider redundancy, so like creating multiple systems doing the same, if you partition the system wrong way and you deploy it in a specific way, you cannot really implement redundancy afterwards. That means you have to go to the beginning and design the system from the scratch. Of course you can do it, but you will need to refactor like most of the system. So typically all the kind of dependable features cannot be like afterthought. You need to really do that from the beginning, and that's why designing those systems, specifically embedded systems, is very important. And when it comes to dependable system, there are different standards how this is defined, but we typically consider security, confidentiality, safety, reliability, repairability, and availability. And there are definitions for all of those. But what is important here is that you have to, I think I like the definition, that dependable means that it's intended service, so it provides intended service with high probability and does not cause any harm. So if you consider safety, for example, you don't want to kill people and you don't want to create like environmental disasters. Think nuclear plants, right? If you have a nuclear plant, because you might make the system very safe, that everybody will be evacuated, evacuated, there's no human killed, and no one can enter the area for next 100 years, right? This is unsafe system. So it's, you don't really want to kill people, you don't want to do harm people, and also you don't want to do harm to the environment. And of course, the most secure system is the one, is the one that is disconnected. And the safe is the one that never starts. This is of course a joke. The system that never starts is not really usable, right? But it is safe. Also, when we talk about safety, we cannot really say that the system is 100% safe. We should also be aware of that. So if you have a car, when the manufacturer estimates the, let's say, deployment of an airbag, they say that 99,9 is going to be deployed correctly. And then you wonder what happens in this 0.01%. They allocate money for lawyers. Because they know that this 0.0% it will go wrong. Right? It's the same with nuclear power plants and planes. Almost 100% everything will go well. But sometimes might not. So we should always be aware of it. It's the same with trains and so on. So we create those systems to be safe, but yeah, it's the same with security. Security can be broken for different reasons. So we now actually have a law that probably, I don't know, you noticed, have you received an email about security breach? I mean, if you register now into somebody's database, a system, they have legal obligation to inform you that your data being leaked, right? And that's by law, because you cannot guarantee that the data is secure forever. It doesn't exist. It's 99.9% is secure, but accidents will happen. It's the same like if you look at the server availability, they will typically say 99% something is available. But sometimes they have to shut down the server for maintenance. So they will try to guarantee as much availability to you as possible, but it's not like 100% error. That's hard. Oh yeah. Even rockets, you know, we had accidents with those as well. So. Another very important thing, so it's not only about dependability, it's also about timing correctness. So cyber-physical systems have real-time constraints. And there's also kind of specific to cyber-physical systems and the environment they react to. Because when you look from control engineering, from kind of how you design and use systems, you will have certain requirements how fast or slow you need to react to the environment. I mean, a normal example in a car is that when you brake, you want your car to stop, right? So when you press the brake in your car, eventually it will stop after, let's say, 20 meters, depending on the speed, tires, and things like that. But in cyber-physical systems, we have hard and soft deadlines. So if there was a wall in your car and the wall is in 20 meters, you really want your car to stop before 20 meters, right? If it stops after, it's too late. There's actually infamous brand that had problem with that. Can you guess what? You know that there was actually cartoons with the car that eventually stops? Toyota. Toyota had an infamous bug that the car, I don't know which one, I think it was Prius, that had a problem with brakes. So that's why people say eventually stops, but you don't know when, but eventually is. There was a bug, and actually a few of those had so. Especially when they introduced like drive or fly by wire, where people said, okay, now we are so great with our electronics that we don't need any physical connections, everything done through networks and buses. So then, if the brake pedal doesn't work and is not physically connected, you just rely on the network to send the signal to the brakes and stop, right? And there's a lot of things that could go wrong. But what is very important in cyber-physical systems, coming back, is that actually things happen on time. So it's not like with your Windows when you want to, let's say, shut down the computer and you wait 10 seconds and eventually it will kind of stop. In embedded systems, you have to guarantee that things happen on time. Like if you control a nuclear reactor, there are certain processes that need to happen in a certain time window. If you are late, the core might explode, right? Actually, it happens in the past, so don't try it. So there are also soft constraints that says, okay, if you don't do it on time, it's bad, but we are going to survive that. So we typically, there's also a third one firm, is more about it later when we come to scheduling. But typically, certain processes inside the physical systems need to meet the deadline, so they have to happen within a time window. So, and this is really, really important. And unfortunately, in software, that's not really true. It's not been taken into account because when you model traditional software, the one that run personal computer servers, lacks this notion of time. You basically, typically, you think about throughput, average time, and the best performance. Whereas in the case of real-time constraints, you are not interested in the average or the best kind of characteristic. You are interested in the worst case. And of course, that's the one that people don't really want to talk about because from hardware perspective, it's really bad to talk about worst case scenario because this is the slowest the thing can be. And if you consider that, you cannot really sell anything. Because you can say, okay, my computer on average runs with, let's say, 5 gigahertz. Yes, with perfect conditions. When there's nothing else is running, you have one thread and one task running, there's no concurrency and so on. And now let's consider a case where I want to get the worst case. When the system is fully loaded, it's hot, basically, so the cooling doesn't work, and it starts throttling. And suddenly, oh, it runs only 1 gigahertz. Okay, and this is the time really your computer performs. It's the same with the phones. That's how they cheat the benchmark, right? They say this chip runs whatever, something, number of points in the benchmark. Yeah, and it does it for 3 seconds. And you run actually any benchmark for 1 hour, it will just slow down to not really great numbers because it starts throttling, and there's various reasons for that. One is energy and heat. So anyway, and as you probably know, or maybe you remember still, hardware actually have a sophisticated architecture design with pipelines and caches. And those typically improve average performance and makes the worst performance worse. So actually the advance in hardware doesn't improve the worst case scenarios, but they improve the average and the best case. The other problem is that we typically, I kind of mentioned that a bit, is there's a mismatch between the digital world, the physical one, and the digital, so it's the cyber world. So that's typically because you have a digital and analog parts. The physical world is continuous domain. Things are analog. We don't distinguish between points. Yes, we have atoms, electrons, quarks, whatever. So you're using distance. Yes, it might be discrete, but what we observe typically is continuous, right? However, our realizations of the control systems on hardware are discrete and digital. They run in quantified amount of times, ticks of the clock of the processor and so on. However, when we design the systems, control loops, we typically have to cope with the plant which is physical. So there is a mismatch. So the things that you run actually on the computer, so that's actually feedback, and the plant, which is the physical one, has an issue because you have to discretize the things. That's the discussion on the ADCs and DACs. You have to transfer the continuous system, like voltages, into values that are discrete in time. And that causes a lot of issues as well. I don't think we're actually going to go in details. This is very important if you start designing control loops. Really control. Anyone from the Rocket Club? So if you go to the Rocket Club, they're actually going to have a lot of challenges with it. Something where you have to control things fast. For example. But yeah, this can get really sophisticated. the plants or the things you need to observe happens fast, you have to have a corresponding digital part that can also cope with that. And the problem is that again, coming from software, so pure software, we don't really have a good mechanism for handling that. So, at least from software engineering perspective. Good. Another challenge is that we must use resources efficiently. So if you consider traditional systems, like a server, you just deploy it to a server and you hope that you have enough processing power to run your application, right? When it comes to cyber physical systems and embedded systems, so something also like running on 8-bit, it becomes obvious. The speed is 1 megahertz. The memory is 64 kilobytes of RAM. And also the peripherals, the resources we have available are lower. But there's also other aspects that are very important, like energy. Typically when you perform high computation in the cloud, who cares? Now LLMs, who cares? In embedded systems, you actually care a lot. Because first of all, the devices are run on batteries, at least in some cases. So running, for example, your application full power on this device makes you very unhappy because your battery will last some hours, not days. The other thing is that it will make your system hot. And why do we don't like that? When things get hot? Yes, it impacts performance. Performance goes low. Next. What's the other thing that is not so obvious?
It wears the hardware out.
Yeah. It actually can age the silicon faster. And another one. Yeah, it's a waste of energy, but there's actually one other thing that normally people don't think about. Yeah, well, that's the aging part is. It can actually break faster. Okay, that's actually a simpler one. What happens when your processor gets hot? What do you need?
More heat, cooling.
Yeah, you need cooling. It costs money. So you spend more energy to consume energy, and then you put extra energy to cool it. This seems stupid, right? Yeah, so don't do that. For example, if you start using, actually the high-performance gaming phones, actually they have kind of liquid cooling, right? Because otherwise it starts throttling. So heat actually causes problems. So you actually use the energy to, liquid cooling is kind of smart because there is actually the heat to transfer the energy. But typically, like on the computer, you will use energy to actually, you use the computer, the process cycles to consume energy, and then actually you put on top extra energy to cool your case and your computer. So it's kind of double waste. So sometimes actually it's a good idea to design software well. So of course we also want to have environments that kind of perform well. One of the actually different designs is that we can design software or runtimes in a way that matches the hardware architecture. So we don't really want to waste the processor cycles. That's like design patterns, actually anti-pattern. So busy waiting. Have you heard that? Busy waiting? So you normally don't do that. You actually put the computer into sleep. You don't wait in a loop for things to happen. I'm pretty sure Tommy should mention that. So you don't burn processor cycles doing nothing. You of course want to enable optimizations and use the algorithms that kind of more kind of suitable for the work you want to do. And there are also different hardware architectures that are better at doing one thing than the other. Then when it comes to code size, of course it matters, especially if you consider embedded systems, because everything gets integrated into one chip. So if you consider your personal computer is going to have a separate memory chips, and actually they will come with modules, you can change them, you can upgrade your memory, whereas like a computer like that comes with predefined set of memory. Of course, during production design, you can decide how much memory you want, but they will come with maximum few megabytes, right? Commodore 64 has 64 kilobytes of memory, and we're still able to write operating systems. Come on. Of course, they were running from floppy and they were loading, but we were able to do that. So it's a bit funny when people complain, I have 32 gigabytes of RAM and there's not enough memory. Come on, there's plenty of memory, just don't use it efficiently. So that's really a constraint, and typically you can use either different programming languages, different approaches to actually reduce the code size. And that's typically is required. What's the easiest way to reduce size when you build C and C++ program? What do you do to reduce code size of C or C++ program? Yeah. You enable optimization. People typically forget about it. We have something called optimization. And there are different types of optimizations, also for size, not only for performance. And on embedded systems, typically the optimization for size also improves performance. Why? Why optimization for size optimizes performance? It's very common. Yeah?
For performance, that because you have, in order to reduce the actual size, you have to program it so it's closer to machine code, which means that it's less humanly.
It's actually simpler.
Freed up more memory.
Yes, actually, the program gets more compact. More compact means less instructions. So we will actually, it seems, it's typically when you turn optimizations, depending on optimizations, it can blow the code size by, for example, avoiding loops. But not all loops are bad. If you can execute the program in very small compact memory size, actually you can do branches and jumps that are fast. And on different architectures, typically making it small also packs the code so it fits caches. If the code fits caches, it executes extremely fast. So that's why actually having code that is smaller typically performs also better. But it depends on the architecture. So, okay, the resources is also a weight. This is also typically if you have a phone, you don't. I mean, have you seen the first mobile phones that were available? Mobile, that was size of a brick. Yes. So back then it was very important to use the resources efficiently because making it the battery bigger because it will actually make it really heavy. Nowadays it's not so case, but in certain applications this is important. So again, heat sinks, if you can build a system without heat sinks so it doesn't get hot, it's also an advantage. Because it's actually lower weight. If you think about things flying, right? For example, it's important like drones. And of course cost, so again, less resources you use, it gets less costly. Typically, cost of memory, cost of hardware is related to the cost of silicon and the manufacturing process. So if you can use less hardware, less memory, it will make the product cheaper. And with the system on chip, so actually processor integrated with memory and all dedicated peripherals, you can really reduce the cost significantly. So that's actually the reason we see microcontroller used everywhere. I mean, the cost of microcontroller is less than $1, right? It can be actually cents. I don't want to lie, but I think the cheapest processors, RISC processors from China are like cents now. So they basically virtually cost nothing. And that's actually also one of the reasons, like the processor 6502 are still used in some of the very, very cheap Chinese toys, for example, because they virtually cost nothing. If you see those toys with this black blob, some actually they have it. There's a very cheap way to actually produce them because they actually put just on the board and they're just protected. It costs nothing and still it implements a basic microcontroller. So. Good. So common characteristic. So cyber physical systems and IoT systems use sensors and actuators, already mentioned. Typically in IoT they are connected to internet. Some physical systems can be connected, but that's not the predominant kind of feature. In Internet of Things devices, they need to be divided, and they actually system performs the function for a number of connected kind of devices, IoT devices, whereas in cyber physical systems, we normally actually have a dedicated system for controlling certain things, but this distinction, I would say, is getting blurry nowadays. What is important is that embedded systems are reactive, so they typically react to the environment and they interact with the environment in the speed that is, or the pace that is determined by the environment. So depending what you control, where you walk, the actually speed will be adjusted. So if you think about control panel, like heating system, right from Danfoss that is on the wall, how fast do you need to react? So you have a control panel on the wall. Why? Yeah, so it's if meaning if there is alarm, for example, if something happens to anything. In principle, all those devices sleep like 90% of time. They do nothing because they only display stuff when you actually press them or you do something to them. Otherwise, I mean, if you want to have online available system, you want to show events and things like that, maybe, but user interface is slow. Because why? Humans are slow. I mean, how often do you read the screen? How often do you press a button? Right? But now imagine you have something that rotates. Like you have air conditioning home. When they're controlling the motor in the air conditioning, it has to be relatively fast. And of course it will run only when the air conditioning is on, but while it's running, you want to make sure that actually the engine is controlled. So the speed is maintained, the torque and the forces are maintained so it doesn't get destroyed. So in this case, you will run with some kilowatts, right? Standard frequency converter at Danfoss runs around 20 kilowatts speed, and you have to get adjusted to that. And again, it depends on the application, because there are faster ones where you have to actually react fast. Ventilation, again, if you have like HVAC here, it's typically quite slow. Still, the motor for controlling the flow might be kind of a bit challenging, but humans, the environment actually that we live in will get adjusted slowly, and they know that. So the temperature actually and the ventilation in those rooms is not going to get, I mean, it will not change fast. But controlling the motor in the system itself actually changes. Okay, I lost my mic. So another important thing I mentioned is that those systems are dedicated. So they really are tuned to perform the function they need. Of course, there's this joke, can it run DOM? Do you know that? Yes. So typically you will run only the software that you intended to. So on the washing machine, on the fridge, you will run software for the fridge or washing machine. But of course you can hack it. And probably if it has a display and input output, whatever keys, something you can control it, it will run too. This is a common joke, and yeah, they had it on medical devices, basically everything that has any open interface and allows you to program, people will try to hack it to actually run it. And why do?
I heard it at one point, but
It's very well optimized game.
To work on a USB stick.
It can run on anything.
But USB cable, charging cable, because that's more like a controller to control the energy flow.
Yeah.
So
The thing is that
can it run on that?
Doom is implemented in C. I mean, there is a different implementations, but there's one that runs, is kind of ported to C. It's very well optimized, so it can run like on potato, basically. It can run on anything. And it's still cool because it's kind of 3D game, right? So it seems like very advanced game. It was back in the time. And of course, normally those devices don't use keyboard and mice and so on because they really have a dedicated user interface. Most cases, they lack any interface. The only interface typically in those devices is a debug interface that is burnt when it goes into production. So as soon the product leaves production, those interfaces that allow you to communicate are burned, at least from developers' point of view. And the only one that you can have is the user interface that is actually planned for the product. It is planned. So if you compare the embedded system and desktop kind of server systems, when it comes, for example, one very important thing on PC is the compatibility to x86 Intel architecture. Why is it important? So the PC server life, this is very relevant, the compatibility to x86. Why is it important?
Because it offers the most common instructions.
It's actually about applications. The instructions on 886 are actually bad nowadays because they actually originate from 880, 888 and so on, and there were extensions of those. And typically the applications that are built actually for those, like Windows DOS, they require x86. This is probably not as relevant nowadays, but still there's tons of applications built for that architecture, and that's why it was so important. Do you remember where Mac or Apple actually changed hardware from Intel to ARM based? Basically all applications had to be rebuilt. That caused a lot of issues at the beginning, right? I mean, there's still some applications that don't really run on ARM. And that's because you cannot easily rebuild like all applications from one architecture to another, because they depend on a lot of components. So architecture, whether it's fixed or not, on PCs, yes. On embedded systems, not, because the architecture actually needs to fit a specific requirements and the environment you're controlling. Models of computation. Who remembers von Neumann? What's von Neumann? And the other one is called Howard. What's the difference? Okay, in von Neumann, the program and data is stored in the same memory address space. That's how PC works. That's why you can easily make viruses. Because I can make a program that affects other programs and also can change data. On Howard architectures and modern embedded systems, we have different ones. So you can store program data separately. If you go into like various different architectures, FPGA, DSPs, this gets even more interesting. So there's not like one memory space where everything runs, for example. Those systems are interconnected in very different ways. The optimization objectives, as you mentioned, the standard PC and server really is optimized for average performance or best performance, whereas when it comes for embedded, there are different targets. So there are multiple ones, like the energy size and the worst case scenario when it comes to real time. When safety critical, in PC, no one cares. I mean, if your PC stops working or responds or application crashes, you can easily restart. On embedded, possible is very important. And if something goes wrong, typically you need to reach a safe state. Right? It's not okay to display screen of death. This is not okay. If your system crashes, you have to safely stop your application. So, like if your dishwasher or washing machine stops, you want still the water to be pumped out. Right? You don't want to somebody open the washing machine full of water. So there are some things you have to really take care of sometimes. Embedded systems are real-time relevant, whereas PCs are not. They are not built for that. And the apps know the design time. So, yeah. At design time, you know, okay, you have to be x86 compatible, and you want to use here a word, right? But when it comes actually to embedded, you have to, at design time, know more or less everything. You know what operating system you want to know, what applications and what requirements you need to fulfill. So you know everything at design time, not actually afterwards. It's not general purpose computer. Yeah, so when you really think about embedded systems from like education perspective, teaching, there's a lot of different courses you can do. So of course, in the undergraduate program, you learn about programming, you learn about algorithms, right? You do that this semester. You had a bit about computers, operating systems, you had the math. They actually claim you should have some electronics engineering basics, architecture, maybe not so, and then you should do project, labs, exercises, and so on. If you go to graduate programs and you really want to get kind of into embedded systems, you should also look into control systems that I mentioned, real-time system, robotics, middleware, and so on. So you can explore a lot of different topics. All of those actually are relevant for embedded systems. As mentioned at the beginning, we actually going to follow like a flow suggested in one of the books. It's not really important what the boxes are, but what is important is that you have different boxes. So in order really to design any application, you have to understand the application, you have to have knowledge of the application. You cannot design an embedded system for something you don't know. And that means you then have to look into specifications, that you have to have repositories of different hardware, component solutions, and software systems like operating systems that finally will contribute to a repository of all possible designs. You, for example, learn about design patterns. Nowadays, you don't design software purely from scratch. Okay? And that's why AI is also good at doing software. Because what you do, you actually design new software based on software that has been done in the past. And you learn about some design tricks and some ways of designing and programming software systems that people done in the past, like object-oriented programming, right? Has been invented 40 years ago or more. So you learn the things and then you use that to build the applications. So as mentioned actually on the diagram, what is also important in embedded systems, and I mentioned, is that optimization. So part of the application mapping, so actually mapping your application requirements to the different let's say building blocks in the design repository, it's important that you also optimize. So you have to run this probably several times through the design process to find implementations that optimize the general goal and requirements of the application. And testing, as stressed many times during the semester projects, testing and validation is very important. When it comes to embedded systems, it's even more important, because when your system is deployed once, how do you fix it when you find a bug? Yes, exactly. You do a recall. Yes, that's what actually happens sometimes to the car manufacturer, right? Few million cars go back to workshops, and the producer pays for fixing them. So it's really bad. So that's why you always have to test and validate your product before it goes to market. You cannot fix easily things afterwards. But actually now, with all the products connected, it's kind of a must. But because, again, we have legislation coming like Cybersecurity Act, this gets very interesting because product will need to be maintained for the years that are on the market. So that means you continuously test and check for vulnerabilities and patch those systems. So, some problems to solve, or questions, to force reflections. What's the difference between embedded systems and cyber-physical systems?
Cyber-physical takes both hardware and software into consideration. Embedded systems is more just focusing on the hardware.
Embedded system is part of cyber-physical system. Embedded system consists of hardware and software. Cyber-physical system also contains the physical part. So embedded system, the hardware, software alone is not enough. You also have to know the plant. So you have to know the real thing that you control. Yes?
Could you just give another example of this?
For what?
For these hyperphysical system, like saying like, okay, this is basically embedded topologies into some environment.
If you consider any product nowadays, so electrical kettle. So you take a kettle that actually boils water. There is, if you have anything that controls the temperature, for example, I have one that I can set 90 degrees. So there will be embedded systems, meaning microcontroller with software running, that will read the temperature and control relay to control the electricity that goes to the heater. So the embedded systems is the chip and the software with the pins going to the sensors and the relay problem. And then you have the physical plant, and the physical plant will be the one responsible, the container for the water, the heater that's actually heating the water, and the relay that controls and turns it on and off. And there will be also a sensor. And this is the physical kind of phenomenon.
Also,
that you
the
could-
sensor wouldn't be part of the embedded system.
It depends how it's done. If it's digital, it's kind of on the border. But there are also, you can create it, I mean this one, if you really need to know the temperature, I mean I can adjust the temperature. Because in the old days, temperature sensors were very simple. It was actually typically a metal that was expanding with the temperature rise and was disconnecting actually the relay. So depending on the implementation. But yes, if you can adjust the temperature, then there will be actually a digital one that will transform the heat into some discrete values connected to the microcontroller. However, that's not going to be the chip. It depends on the price. So they are cheap, and typically in those products you find on the market, they are done very, very cheap. So if it says 90 degrees, you shouldn't believe it's 90 degrees. It's plus minus 5 or 10 degrees. So it depends how well it's done. Because typically they actually come with price. And why price is important? Because for you, this is actually an interesting consideration. If you make, I mean, if you consider a product and you say, by doing the sensor, right? Very simple, like using thermoresistor, I lower the price by 10 cents. Is it a lot of money? So you save 10 cents.
Per unit, it is not a lot.
Yeah, exactly.
Want to produce like a million or a couple of million.
And that's actually the issue. So that's why they make cheaply, because they know they produce millions of those. And if they sell 10 cents, they actually save a lot of money. So it's always kind of the same with the microcontrollers. That's why they go for very cheap solutions. But typically the embedded system is the one that implements the discrete part, the digital part, and then the physical one is the one that is analog. And that would be actually the heater, the water container, the water itself, right? That would be the physical environment you need to control.
So depending on the sensor, are there sensors that can read to digital directly?
Yes.
So if
The integrated sensor.
would be the embedded system.
You can have an integrated sensor that actually communicates with the microcontrollers through actually like I2C or SPI. But the cheapest way is to use a very cheap microcontroller with built-in ADC and like thermoresistor. And the cheapest one is to actually use like binary on-off based on some temperature expansion kind of phenomenon. So it's actually when the temperature is low, typically it connects a circuit. When the temperature reaches a certain limit, it will disconnect. Okay, that was first question. We have more. Too fast. What is hard timing constraint and the software timing constraint? It's like slowly dying. Yeah?
If I remember this correctly, there was something related to operating systems, like not a Lisp, where like you had a hard real-time operating system and a software time operating
Yeah.
system.
But why?
Like basically, some things should happen like immediately, basically, like really immediately, and there can be a certain delay, like it depends on what you use for.
Yeah, so typically in the systems you have deadlines. So typically in any system you design that has timing constraints, you will need to meet deadlines. Deadline means that something has to happen within a time window. And it can be actually funny because often we think our time window like it has to happen before. This is typically safe, but typical systems have something that, okay, it happen before and after. Sometimes things happening too soon is also not good. But what is important that in the hard real-time systems, so hard constraints, so with hard deadlines, you have to kind of generate the output, or you have to finish computations within the time window or before the deadline. If you don't do it, it can result in catastrophic consequences, like the car not stopping before warning, right? In a soft timing constraints, you still should finish the calculations or you should observe timing before the deadline, but if you don't, the user probably is not going to be happy, but there is no damage done. So that's the difference. So again, if we think about nuclear power plant, if you don't really control the core well, it can, I mean, the result might be that something explodes and there's a really huge kind of damage to the environment and some people can die, right? But you think about operating system and Windows, if you cannot close a window and you have to wait 10 seconds more, there's no really actually damage done. So why are we interested in energy-aware computing?
Both to decrease our carbon footprint, but also to decrease the heat produced by the hardware.
So we interested in energy-aware computing because we don't want the system to consume too much. Yeah, of course. That will be another one. Especially if you consider if it's again one product, no one cares. But if you have millions of those, then you start caring, even about 1 watt. The other thing is that electronics can get hot, and that also increases fan of cost. So what's a reactive system? That's not the reaction.
A reactive system is basically a system that reacts to its environment.
Yes, so the reactive system actually is the one that kind of continuously reacts to the environment and it actually reacts with the pace of the environment. That's very important. So the embedded system part, the hardware and software part needs to be aware of the speed of the environment, has to be able to react to it. And what's the main difference between PC application and embedded application? Yes?
PC applications can and will often be changed, where embedded systems there are limits to how often you can update it,
Yeah.
maintain it, essentially.
Something else? Yeah.
It's not asking, for example, how many resources that PC applications are using, but for embedded it's really important because of energy, space, and everything.
Correct. Another thing?
Most times embedded systems are made around the application as well, while PC generally.
Yeah. So the embedded applications are really dedicated ones. That means you actually know what you're doing at design time. You don't change the application afterwards. Good? So let's have a break. Yeah? Like, you can think about any system that has a reaction to the environment. So if you think about the electronic kettle that boils the water, you have to make sure that you're actually heating up the water. So you have to, at a certain point of time, you have to react to stop boiling. If you continue, it's just, the water will evaporate, right? So the reactive system in this case is the one that has to react with the speed of increasing the temperature.